Welcome back. Hopefully everybody is doing well, happy, healthy. And today I'm going to share my screen, discuss more detail about embedded system and the internal organization of embedded system. I've discussed the definition of embedded system last week for you. And here is the learning objective or learning outcome from this lecture. I'm going to look at the operation of major components of the computer. Inside the computer, we've got like 3 major components. And of course, as I said before, couple of sub-modules or maybe minor modules or devices inside the computer. When I say computer, it could be even ECU inside your vehicle. If you are looking at any other industrial application, it could be the application of the computer in any other automated system, okay? So it's not only automotive, it's not only the computers in front of you, any devices, any electronic devices having a computer inside supposed to have this major and minor sections in order to exchange information with the CPU, which is the brain of your computer. Later inside the automotive, we call it ECU. We do not have the exact structure or exact format computer inside ECU. ECU stands for what? Who knows that? ECU inside the vehicle stands for what? Yes. Control. Exactly, electronic control unit. And that's what we call it, the computer or the brain or the main processor inside the automotive. Every single component, such as input output, every single sensors, electronic devices that they're supposed to receive command and function in order to give us either safety. Remember last week I said some of the functions are for safety, some of them for sustainability, some of them for luxury convenience, or we call them in their fun. All of them are receiving command on their ECU. They are communicating with ECU, right? So that's why today we are going to look at this part, which is the major component of the computer. And then I'm gonna look at the memory structure of the computer inside the lab. Also, I'm gonna open it up with more detail. What is the organization for the microcontroller we have inside the lab, right? So, and then what is the role of CPU? And of course, if you would like to study a little bit this information with detail, go check chapter 1 of the reference book, right? So let's start with the big picture. Last week I've covered the embedded system for you. Today I'm looking at the microcontroller and the computational system and all the detail that I just explained them to you. So remember, during the lab I've introduced, we are going to bitwise some of the information for the microcontroller. Suppose I'm having like multiple switches, I'm having multiple LEDs, and I'm going to at a time only turn on or off some of them. Who can remember that bitwise in information? And I told you we've got multiple methods in order to customize the functionality of some devices connected to the same port. Remember all those little switches? They are connected to port T of my microcontroller inside the lab. But how many switches I have in there? I've got like 8 of them. So now, I'm gonna now explain it in more detail. For every single port, I've got like 8 bits. If this is an 8-bit, let me open up some text file in here for you to write. Every 8 bits is called a byte, right? Hopefully everybody can recall this from last lecture. If not, go there and update yourself one more time. So I'm gonna just maximize this and use it in here for you. So suppose I'm having 8 bits right in here. something like this. 1, 2, 3, 4, 5, 6, 7. So every single one is called a bit, right? And now, if I'm having 4 of these bits, what do I call it? A nibble. Bit is the smallest. Keep it in mind. How many bits I have? 8 of them. 4 of them is called a nibble. Now, if I considered 8 of them, this is 4 of them, this is 8 of them, and this is only 1. So 4 is a nibble, and then 8 of them is called a byte. Byte still is not the largest one. Now, suppose I've got 2 bytes, means I have another one of these guys right in here. Another 8 bits right in here. And then in that condition, I'm having how many? 16. If I have 16 what? 16 bits. If I'm having 16 bits, what do I call it? I call it a word. And now this is the largest. So now you have a good understanding. The smallest piece of the memory is a bit. And then 4 of them nibble, 8 of them bytes. And then if I have 2 bytes or 16 bits, we call it a word, which is the largest size of the memory. Why do I need to learn them? Because memory is addressed based on this information. Of course, we never bring up the size of the memory with bits. We usually don't bring it up with like even nibble, not even word. We usually address it with byte, right? This one. Or maybe if it is a huge one, we can just say each byte, what is each byte? Each byte is 2 to the power of 0. Now, if I have a bigger memory, then I have to go for, let's say, 2 to the power of 10, which is a kilobyte. And usually a kilobyte is 1024, and this is kilobyte. And then I have like megabyte. Megabyte is 2 to the power of 10. Then I have giga, 2 to the power of 30. And usually the 2 to the power of 30 is giga. This one is mega. And I have the biggest one, terabyte, which is 2 to the power of 40. So we need to learn this information because the size of the memory is being addressed through this unit, not maybe any other things. So have this in mind. And then remember last week when I was teaching you how to convert binary to decimal or to hex, I introduced least significant bits and most significant bits. I have it also in here, most and least. Now, still we need to consider them. Most significant bit is the first non-zero bit from left. From left, the very first one, which is non-zero, we call it most significant bit. And otherwise, first bit from right, still I'm considering a 8-bit. First bit from right, from here, is gonna be last significant bit. And again, it has to be from right. From right, it's okay if it is 0, right? If it is 0, still we call it, it could be 0, but here couldn't be 0. Remember, even when I was just teaching that each time that you are going to convert binary to hex, if you do have less than 2 digits at the right, you are more than welcome to add 0 and create a group of 4, because 0 on the right is 0. Therefore, in here, if I'm looking for most, it must be non-zero. So far, so good. Yeah. Now, it's time to go learn about the structure of the computer. Remember at the beginning, I said, every single computer system, it has 3 major parts. What are those major parts? Regardless, we always have CPU. This is CPU. CPU again, central processing unit, same as us as human. What is our CPU? Our brain, right? CPU is where every single sensor, input output for us, our eyes. How many input sensor we have as human? 5 sensory, right? We've got listening, we've got seeing, we've got tasting, right? We've got touching. So all of those are going to brain. They are sending a signal to my brain, to your brain. And then brain is processing those inputs and accordingly will generate an output signal or output command for our actuator, which is arm and leg. Same here. I'm having CPU, which is central processing unit. CPU by itself doesn't do just anything for me. CPU is supposed to receive information from some input and output. So now, under CPU, which is one of the major parts of the computer, I have to have some memory. For us, I wish I have my brain demo to show you. For us, where is our memory center? Right here. We call it cerebellum in brain. We have a memory sensor, memory center. Every single information is going to a center right in here. And that's why many of us are going through childhood trauma, because everything is stored right in here. With computer, the same. Everything is going to the CPU and it will stay in there until we adjust it, we remove it, we edit it, because they have memory. Some memories are random memory, temporary memory, like your USB and stuff. So as soon as you disconnect your USB from the computer, those information doesn't have anything to do with the CPU because they are disconnected. But there are internal memory. For that internal memory, any information is being sent to the computer and you do not want it to be there anymore. Of course, this is your job as a user to adjust it, to remove it, to delete it if needed. So that's why we say we have RAM and ROM. Who can tell me what is RAM? RAM is, I just said it, yeah? Random access memory. Random access memory like what? I just brought one example up. One is like USBs. What else? We don't really use them nowadays, but back then we had other memory, random memories. Please. Floppy disk. Floppy disk, yeah. Have you ever seen floppy disk? I don't think any of you, because that was the very first version of the memories. Maybe 20 plus years ago. I would say, yeah, 20 plus, maybe even 30 plus years ago. That was the very, and the size, it was like in a way that you can only store one PDF, not more than that. Forever. And then another weird thing about those like memories, most of the time you cannot even remove and store something else. It was just for one-time use. And most of the time also, even if you want to delete it, it was not easy task to delete back then. So another one is ROM. Who can help me with what ROM is? Read-only memory. Read-only memory means I cannot process anything. I just read them. Read-only memory. Who can bring me some example of read-only memory? Any idea? So RAM is using address bus in here. Look at here. RAM is connected to address bus, which is one of the minor part. Address bus is a line of communication between RAM and some of the input output with, we always need this line of communication. Sometimes we call it electric line or a line, circuit line. People may call it differently, but usually it's called address bus. This bus is a method of communication between RAM, ROM, all of input output. It could be many input output with the CPU. That's the only, I would say, way of communication for CPU. CPU without bus cannot communicate, send or receive any information from external devices. So RAM is connected to address bus to talk to the chip. We do inside here, we do have some chip to talk to the chip of the CPU. And then we have ROM, and then anything else connected to different pins here on the address bus are input or output. Some of the devices could be both input and output. Some of the devices are only input or only output. Here I'm having some example for you. Printer is input or output. Printer is output, but there are printers that they do have a scanner attached to the same unit. Also, they are single unit. Some portion of it is a scanner, some portion of it is printer. It's a single unit, but it's two different devices. The scanner part of it is input, but the printer part of it is output. So both of them, when we connect them, I'm not pretty sure how many of you have this experience to assign a printer as an input or a scanner, a printer as an output and a scanner as an input to your computer. You have to go through your computer system, define input output in there in order to be able, for example, I have one printer in the printer room and has a scanner attached to it. I have to define it to this computer to be able to send something. If I don't define it, means they are not connected to this bus. Adding like extra electronic devices could be done through either Wi-Fi, which is wireless method, or it could be done through cables. Like for example, we have one printer room back there. We don't have to just have like long cables, like trip all over the space. That's why we connect that to Wi-Fi. And this computer in here is connected to the same Wi-Fi. Still, they do have some bus to communicate through Wi-Fi, right? So now we do have like monitor. Monitor is input or output? Always output, like LCD. LCD can never be in your lab setup. LCD could never be an LCD in the lab setup. It was connected to port P. I just bring it up as an reminder, and so on. Keyboard, it can never be output. Keyboard is always input. Mouse is always input. My pen is always input. All of them are connected to the same bus. But the major part in here is just CPU RAM or CPU input memory. This is the memory part. Input output, all of this also, they are devices that can communicate with the CPU to exchange information. So they are connected to three minor part or minor section. They're supposed to be connected to address bus, right? Some of them to both control bus and data bus as well. So we have address bus. Address bus helps to transfer memory address. Address bus is transferring memory address. Memory address like what? Like for example, on the computer, we may have different driver. Do you know that? We have different driver. Like for example, in this computer, I'm gonna click in here. So we have different driver. Each of the information might be stored under some of this driver, not all of them. If you want to adjust, if you want to remove, if you want to install something new, you have to be able to install it in one of these drivers. If your driver is full, means memory doesn't have enough space for that, you won't be able to install. So we have to store them under a certain address. In the microcontroller that we have in the lab, last week I taught you, every port has some address. You cannot randomly call port P, or you don't know how. If you don't know how to call port P, you have to go get it from the family of that certain microcontroller. I told you in there, if you look at the schematic, inside the schematic, port T is just shown with PT. But if you look at the microcontroller family or the header file for the microcontroller, the same port T might be like this, PTT. In that, PT stands for port, and this T stands for the port name. Makes sense now? So there should be some address. There should be some location for every piece of information not to go wrong with that. So far, so good? Now, let's look at the CPU. CPU stands for control. I just said it. Processing unit. CPU, we have like different parts of the CPU to be assigned to different input, output, and those input, output might be either analog, digital, and everything, right? So look at this one. This is a ROM chip. So this is a chip number 2728. So for example, in here, do you need to understand all of this while programming? Not necessarily, but if you are a designer and you need to understand how much space you need in order to process a complex program, of course, you have to check, do you have RAM? For example, I remember during my PhD, I was designing a 3D model of battery. I was okay until I was designing a single cell. Inside this cell phone, you may think you have one battery because it is like a module. You know it as battery, but inside that certain module, there are sometimes hundreds of batteries being connected in series or parallel, or a combination of series and parallel, then being compressed and packed, and then you think that's one battery. That's not one battery. Actually, it might be more. It might be 30, 40, 50 layers of battery being connected. So that's why it's super important to know, like for example, in there, I was defining one single cell, still that was not that much big, so I can compute the CAD model, because inside the CAD model, I had electrical, I had mechanical, and I had material processing. It was okay, but as soon as I started adding more cells, connecting them together to create a full module, I was not able to process such a design using the same regular computer. Then I had to order a fast computer. And fast computer back then, it was above $10,000 in order to be able to process such a huge file. Otherwise, I was using console for such a simulation. I was running the design, and then I had to leave it a week or two, and still it's not done. And after waiting for such a long time, I was receiving an error. Why was that? Because when you mesh, you guys already learned about CAD design. So you know what is mesh. Do you? When you create an object inside a 3D design, you have to mesh it. Means you have to define how accurate you want to be the calculation for that, especially when you are going to look at finite element and all of those analysis. So that's why you need a huge computer for such a process, because every single calculation has to be repeated with the number of those mesh. If you have it like fine mesh, means more calculation. Means you need a huge RAM. Therefore, then you need to, I explain all of those to say why we need this understanding. Because you need to know your computer is capable of processing all of those informations or not. Otherwise, if you are dealing with something simple, not a complex project, a huge file, you are good. You don't need to. Now, how do you understand those stuff? This is a chip, right? And this chip has, look at here, this chip has, this is like the power. This is like lots of them. Anything with A is standing for analog. Anything with D, digital, these are the analog pins. This is the ground. Again, I've got some digital on the other side, and I've got some analog on the other side, right? So in here, I'm having this information from the manufacturer. I didn't measure this. Nobody measured it. It's coming from the manufacturer. This one has like 14 pins A. And then I'm having like 8 D pin. Now you know what is D, what is A. Then I'm having, if you want to calculate the capacity, 2 to the power of pins A times 8 is going to give you the capacity of this chip. The capacity part, as long as you know your address pins and your data pins, if you know the address pin and data pins, you can calculate the capacity yourself. Make sense so far? So now, if you know how to calculate like the capacity, then you can calculate the organization, right? Organization, again, you get like the 16K, this is a formula. This is not my assumption, this is on a standard. 16K times data pin. It could be different for different chips. It depends how many data pin they have. In here, you should say 2 to the power of A pins or address pin times data pin. Here, 16K is just a constant times your data pins. 8 stands for your data pins. That's why it could be different for different chips. Make sense? Any questions so far? Next. One more time, we already talked about RAM and ROM. Random memory, random access memory, and ROM. Look at the structure of this address memory. All of these are again coming from manufacturer. I'm having in here 4 bits, and this is going to be my control. Means I'm having my input output to be in this address. And then I'm having 1K for RAM. So 1K is assigned for input output. Can I increase it? No, not really. I do not have access to increase and say, hey, I'm going to use more input output. Therefore, let me borrow some RAM from this space and assign it to the other space. We cannot customize it. That's why, again, as an engineer, you need to understand how much space you need for processing any complex data. So look at the manufacturer information. In here, this guy is having like 1K for input output, 1K RAM, and 32K flash. This is the structure of this chip. Now, the address is given, and this address also is a standard. I have no access to customize them. That's why I say, look at the data sheet. Address bus is this one. Remember, CPU is supposed to communicate with address bus. All of the inputs or outputs, everything is connected to address bar. But if you look at disk, for example, in here, or look at printer in here, printer is a one-way, but disk is two-way. How do I know? Look at the structure. What do I mean when I say, I'm gonna clean up to make sure you can see what I'm talking about. Look at here, printer is going from data bus to printer. What does it mean? Means it's a one-way communication. Printer is only output, but this could be both. Means this can receive information and it can send out information. You can get some information from the disk or USB as an input, and then you can also store some other information that you already have into the same USB or disk or whatever as an output. Make sense? So it has a two-way communication. It's connected, it's sending and receiving to the data bus. Through the data bus, it has both-way communication. Monitor is one way. So the arrow has only one-way communication. It can only output. You cannot receive anything as an input from this monitor. And so on. But now look at control bus. For control bus is a method of read-write. Read-write is going through the control bus to all of the devices. So information are either read or write. Some of them could be read or write is talking about the same input output. Read is input or output. Read, input. Write, output. Same as C++. Remember FStream in C++ programming? When I use FStream as a library or header file in C++ programming, means I'm trying to use the information in this library to either read other external text file into my program or output some internal information from my programming into external text file. So when I add f stream in there, I have access to use of stream means output file, and if stream means input information from external file. Same in here. When I say some of them in here are connected to control bus, all of them are connected to control bus. Anyway, they are either reading information or writing, but anyway, it must happen through the communication line called control bus. Make sense? So now same in here. I went back to now clarify in here. Look at here, address bus. Everything's supposed to be connected to address bus. Some of the data bus is when I have both way communication. And later in the lab, CAN communication could be under data bus. Remember, CAN communication could be under one way. CAN could be either read or write, or it can be both, read and write. Same in here, that's the data bus. And then read only, write only. Read only, write only, but all of them supposed to go through RAM. And then write in here. How about ROM? ROM is only address bus, data bus, and read. Why is that? ROM is read only. That's why, since ROM is read only memory, I do not have write in here anymore. I cannot write into the RAM. I can only to the ROM. I can only read from ROM. Make sense? So let's look at the CPU in here one more time. These are the information coming always from the manufacturer. For example, I'm gonna look at the information for our chip in the lab. So in there, like the capacity is, if the capacity is 16K, organization now I know is 2K times 8. 2K times 8. And you just take the information from the data. Look at how do I calculate one more time. I calculate based on data point and address pin. Data pin and address pin. If I have the data pin and address pin, I can calculate the capacity for any chip. So let me pause right in here. It's been almost like 40 minutes. If you have any questions so far, ask me. Then we can continue with the type of ROM and RAM. Everyone is still with me? Okay. Kids, so far we looked at the internal structure of the computer, something which none of us can really see it. It's not visible to us unless we open the case or the computer and see what's going on inside there. Even if we open it, we might not really understand it. But about the ROM, remember ROM stands for read-only memory. We have couple of different read-only memories. Some of them even I've included the pictures in here for you. One type is PROM. P stands for programmable ROM. Programmable read-only memory means a one-time programmable by user. Some of the devices that we use, they have only capability to one time just communicate with them, and then they are garbage. We cannot erase the information, and usually those are cheap. Those are not something expensive because we can use them only one time. That's why we say one-time programmable. And then we have another type. Another type is those that it is a little bit more advanced. You can just erase information like USB. Like what else? Hard drive. Many other similar devices. So those we can erase information, and this one is a little bit more expensive. Reason behind it is because of the type of material that they use in order to create or build such a device. They use UV radiation. You cannot use those information. You cannot erase those information simply through your regular computer. Nowadays, nobody uses them as a usual device, but still I'm introducing to you. In order to clean them up, to erase information, you need special UV radiation. You have to expose them to UV radiation, just erase all the information, clean them up, and bring them and use them again. So that's what we call it EPROM. There is another one, a little bit again more expensive. Why is that? Because now I have more option to give it to everybody to use it. We call it EEPROM. This one is easier to use. I do not need those UV radiation. I can use electrically like erasable devices or programmable. So in there, cost is per bit. Means it depends how big is that device. If it's a bigger one, it is more costly. If it is still it could be EEPROM, like this one. This is the EEPROM, like this chip. This chip, I do not need to use UV radiation to erase the information and upload more information. I simply can do it through programming, similar to the microcontroller we have in the lab. And then again, why we say it is like based on number of bit means how big it is. Like the microcontroller we have in the lab is more expensive than the one which is like the Arduino, because Arduino has little bit, less bits, but HCS12 has more bits. Since it has more bits, so it is more expensive. So it's not anymore UV radiation. It's UV EPROM. And next one, again, flash EEPROM. These are the flash memories, like USB flash. USB flash, you can easily, through your computer, just clean them up and then add more information into it, either as input or output, read information or write information. And those are both write and read. And mask ROM. Mask ROM is just a type of IC again. It's not like regular USBs or maybe floppy disk or CD or something like that. It's an IC. And then it's the cheapest ROM. It's the cheapest ROM, and you need like in order to maybe hold some information, 100 of them. Why I say it's the cheapest one? Because it cannot hold like a lot of information. It's a small. The memory is a small. Let's look at some of this memory organization example. But after the break, I'm gonna just pause the recording here. I'm gonna give you a break. And okay, welcome back to the second half of the class. I already introduced how we can calculate the memory, right? Or actually the capacity of the memory or the organization. Let's practice that using this example right in here. Here I have been given a memory which has like 12 address pins. So I would say address pins are 12 based on the question. And I'm having 4 data pins. Data pins are just 4. So these are the A pin, these are the D pins, right? And I have been asked to look at the size of it. Remember how was the equation? I had to exponent data pin times data pins, right? So like that. So I have 2 exponent. How many data address pins I have? I have 12 of them. And 2 to the power of 12, if you use your calculator, it becomes like 4096. And each location of this supposed to data pin means each location supposed to have 4 bits of data. If each location supposed to have 4 bits of data, then I have to say the 4096 times 4, right? It should be something like this. 4K times 4. This is the organization. This is how we calculate the organization. Now next, so this is going to be my part A, calculate the organization. Part B is asking for the capacity. What was the format for capacity? For capacity, I have to now go ahead have like, I already have 16K. So I have 16K bit. Since there is a total of 4K in here, then I have to say it can hold 4 bits of data. It can, each of them, I have in total 16, each of them are like actually total of 4K location. I have total of 4K location. And then I have like the 4 bits. So altogether, I'm going to have like 16K bits. This is going to be the capacity. 16K, 4K, and then each of them, the pins are 4, then it becomes 16K capacity. Make sense? Another example, what if I have 8 pin of data? 8 pin of data for the next 8 pin of data means my D, I have like 8D. This is my 8D. And then I am asked to calculate organization. Now you tell me, how do I calculate organization? I already did it in here. This time instead of 4, I have 8, right? Instead of, in the previous one, this is my 4D. Now I have, my D is 8D. But this time I have the capacity in here. I have like a 520K memory chip. So organization is gonna be this one capacity divided by 8. So it's been given 512K, and then I have 8 data pin. Then I simply can say, okay, 512 divided by 8 is gonna give me 64K. So organization for the memory then, organization for the memory is 64 times 8. 64K times 8. If the capacity is 512, organization is 64 times 8. This is organization. Make sense? So next is internal structure of the CPU. So far, it was generally about the computer. Computer, I already introduced it. What we have in there, we have CPU, we have memory, and we have all those input outputs. Now, let's focus only on what we have inside the CPU, a little bit more detailed. Inside the CPU alone, we have lots of register. When I say the term register, now I'm expecting everybody be familiar and not to think, okay, register is a weird word for me. Why is that? Because during the lab, remember, I said inside the microcontroller, we have different ports. For the one in the lab, we had port P, we had port T, we had port S, and we had port H, 4 ports. Each of those ports, they do have 8 bits. And now each of those are called a register. In fact, I would say register could be another name for ports, but not the regular ports of the computer, but the ports inside the microcontroller. That's why I say now we are focusing on inside the CPU. So register is very similar to ports. We might have different register for every CPU. How? Based on what's the size of that? Of course, every single one of you have heard about the size of it. Like 8 bits, I already said it. The one that we have in the lab is 8-bit. Then some of them are 16-bit, some 32, some 64. For regular computer, it's usually either 32 or 64. You're familiar with that, yeah? For regular computer, most of the time is either of these two. But if you're looking only to a single microcontroller like the one we have in the lab, is 8. Make sense? You know what I'm talking about? So registers are those that we call them ports T in the lab, or we call them port H, or we call them port S or P. We have this registers for the microcontroller in the lab. In general, registers are some location or some temporary information inside the CPU, and the size of that could be either of this. Okay? Now, we have another part of the CPU which is only in charge of mathematical processing or analysis or calculation. So one part, which is the register, is acting like a storage. Another part in here is in charge of, we call it arithmetic or logic unit, in short, ALU. This is where all the mathematical, all the calculation, all the processing, even the one that I introduced last week, logic, all of those and, or, not, nor, all of those stuff are going to be done under this section of the CPU, which is right in here. And usually this is a large size. And that's exactly one of the parts which is defining how valuable or how costly my microcontroller is, or how costly this computer is. Why is that? Because it has to process everything with a certain speed. If it is faster, of course, it is more expensive. Again, because of the material of that chip, because of the number of input outputs, right? And those are the main factor, not the brand only. So that's why in here you can see it as a larger box. And then I have another one, which is counter. Later, when I teach you more of C, I teach you how to define counter. Counter, in fact, is going to give you the option very similar to looping. It's going to give you option to repeat a process, right? But still, you need to define some address for that counter. That's why I say this is connected to address bus. Now, I'm confident when I say address bus, you know what I mean. If this is the CPU, your address bus, I would say, is the main circuit line or main communication line with other RAM, or let's say memory, either RAM or ROM, and inputs, outputs. It could be many of input, output. So this is what we call it, address bus. I call it AB, means address bus. So this is the main line of communication with the CPU. That's why in here I say any counter is defined inside the address box, because it is very important to be directly able to communicate with the CPU. And then I have decoder. Decoder is acting like a translator, is acting like a compiler, right? So that's why decoder in here, this one is a part of controller bus, not address bus anymore. So this is connected to controller. Who can remember what was controller bus? I'm gonna just scroll up, show you right in here. Controller bus is this one. Remember I said some of the information is supposed to be only read, some of them write, right? And that's why it has to communicate through the controller bus. And then I have more in here. So it's decoder is communicating with the CPU through controller bus. And the last one, data bus. Data bus is the one, remember again, from the same picture I just showed you. Data bus is the way of, or the line of communication that can define which device is only input or only output, or it's both input and output. That's where I have to define my data. That's why I say now every register or every port I have must be connected to data bus. Makes sense now? Why? Because data bus is where I can say this is LCD or LED, and this can only be output. This is switch, or this is potentiometer, and this only can be input. Data bus is in charge of detecting I'm having an input or output, or I'm having an device which could be both input and output. That's why all my registers supposed to communicate with the CPU through data bus. Port A, port T in my setup in the lab is switch. Port H is my LEDs. Remember those 10 LEDs? Port S is used for different, port P is LCD, and so on. Port S is used for different things. All of them are communicating with data bus. Next, I'm looking at the exact same microcontroller that we have in the lab. I just introduced a little bit of the register that I have in here. But in addition, first thing first, again, one more time. Our microcontroller in the lab, which is HCS12, common microcontroller for automotive industry, is 8-bit, 16-bit double accumulator. So these are all the ports in there. Accumulator is 16-bit. Register X and Y that you can see in here, this could be used for different application. So I'm having this much space to assign them based on what I am trying to do. A stack, 16-bit, and then counter, 16-bit, and then this one is condition code CCR, 16-bit. So this is the way it's been already structured. I have no option again to release some of the space from one part, add it to another part, and increase, for example, my accumulator size from 8 to 16. I cannot do that. We cannot do that. So, any questions so far? Anything? Everyone doing okay? Now I'm going to look at this example to see how the processor is processing. Well, I wanted to put the value of 21 into register A. 21 into register A. And then I'm going to add value of 42 and 12 to register A. Initially, I'm going to give it 21. Later, I'm going to add 42, and then I'm going to add 12. How do we do that? First, I need to move value of 21H into register A. So the code B0H that you can see right in here. So first I move 21, then B0H becomes my code, right? Then when you add another 42, instead of having, let me clean this up, H is H, and I'm adding 42. Remember those summation, subtraction that we did last week? I'm talking about the same thing. It's exactly the same thing. Those summation, subtraction for decimal point, binary point, hex, numbers, and everything. Now I'm expecting everybody to be able to understand this one. We did all of those basic summation, subtraction to understand this. So initially I put 21 into register A, and then when I add 21 plus 42, it becomes 04. And then when I add 12 to this, still it's the same. Still it's gonna stay when I add when I add another 12, still it's gonna stay the same. So 404 or 04H is a location, kids. This is the location. I'm trying to push information and be based on least significant bit and most significant bit. Either location still is the same location, or it will move to the next location if the previous one is already filled with information. So first I need to move 21 to register A, and then I'm going to move command, and then I move value of 21 to my register A. And then in the location 04H, as a part of the memory, I'm adding 42. And then now you can see how your address are saved in the memory. For example, in here, I'm having like B0 initially. And then I'm adding 8-bit value, which is the code for moving to register 8. 8 is the code to move a register. That's the code. And then right that in there, I have like actually 1400 to be stored. If you do the calculation, it becomes 1400 to be stored in register A. Then after I move your value into location 1401, in here it becomes 1401. You can see it in here as well. So initially B0 is holding, and then when I add another one, this will move to location 1401. If I add 04, because I add one by one, then it is moved to 02. Then I add the actual 42. 42 is moved to another location. This is the memory address. And I'm not doing this manually. I just want you to understand what's going on inside the computer. This is what the compiler is going to do for us. Then I'm adding again 04. And then I add 04. I move to 1404. And then finally I add, the final result is going to be 12 being stored in location 1404. But still the code is 04H. These are what's happening inside the computer. Now, let's just look at the CPU architecture. So we have two types of structure in here. This is important. And probably we keep using it every now and then over the semester. These two are the main architecture for the CPU. One of them is done by Newman, and the other one is Harvard architecture. I'm going to explain them, and I'm going to define what is the difference between them. The Newman architecture, you will have access from CPU to the memory on the same bus. And now you know what is bus. Memory, and again, in here, you can see it's the same bus. All of the accesses are through the same bus. When you are doing read and write, you are using the exact same bus to read and write into the CPU. So the results of processing need to be written on the memory. Then you have a control box or control bus in here. And you have another one in here. And these two are connected. Data and code memory are connected. So you are using the same bus for reading your code, and then the result of the processing needs to be right on the memory. Then you have a control bus, which is controlling read and write at the same time. So this is, in fact, I would say a slow. This is a slow method. I don't recommend it because reading and writing are happening through the same bus. Each time reading and happening, bus is just going through one procedure. Then it has to stop one and then go through the, because at the same time cannot read and write. And that's the reason this is a slow and this is not the preferred method. And they are not using this kind of architecture, especially when they are designing high-speed computers. Makes sense what I said? Reading and writing is happening through the same bus. Bus could do one task at a time. Either it can read or it can write. If both of them are happening through the same bus, when one command is coming, the other is paused. Therefore, the entire process can be completed in a longer time. So it's slow. Now, when they are creating fast processor, those fast computer, remember I said I used to pay $10,000, not me, my supervisor, my PhD supervisor, paid $10,000 back then to buy me a fast computer to be able to compute my model. Those fast computer is not like the one that I'm using right now in the class. Those fast computer, they do have a different architecture in the CPU. They are having different bus for read and write. That's why when a command is coming for reading, one bus is processing that. At the same time, another bus can do another task. Then the same job or the same project, if it is a modeling, 3D design, or any mathematical computation, at the same time, you have two buses to be active. One is doing the read, one is doing the write. At the same time, information are sent to the CPU to process. The other one is at the same time sending back as output. That's why the processor is fast, which we call it Harvard architecture. You can see in here, in Harvard architecture, I have one for data memory, one for code memory. I have two completely separate modules in here to process input and output, or write or in and read. Makes sense? I believe it's easy to understand. Because of the structure, I have two options, or I have two methods of communication to work at the same time. Therefore, everything can be finished faster. That's why those computers are more expensive. Make sense to everybody? So, in fact, it has a lot of pins in order to process all of those information. A lot of input output, more pin. But when we have it to be Newman architecture, we do have less input output pins, and we have only same bus to process everything. Hopefully everybody can understand this. So now, what's the preferred method? The preferred method is always Harvard. It's more expensive, it's faster, and we are usually using 32 to 62 bits processor. But in here, we are using less bit. Less bit means less number of input and output. So far, so good. Next, let's look at Freescale code word here. In here, I'm looking at the low-level language and high-level language. Everybody in C++, first semester, second semester of your program, you've done C++ programming and object-oriented programming. And that's why in here I say C++. It could be C or any other. Any other language like this, we call them high-level language. Why is that? Because they are only computer language. And they are only understandable for computer, not for human. So those are high-level language. And still we do have some low-level language as well. Low-level language are those which are closer to the computer instruction set, which is usually machine code, usually assembly. Assembly is not understandable for us, is it? Assembly is not something that we can understand. So what is machine language? I said it last week again, 0 and 1, or binary. So binary is a set of instructions that a CPU understands it directly. CPU inside, even if we are commanding it with a different language like C++, it will convert everything to 1 and 0. Us, we don't understand 1 and 0. We cannot command it with 1 and 0. We go ahead and say, for example, cout something. Cout is a command that we can understand it, but inside the CPU, that cout command will be translated to 1 and 0. Then computer can understand it. Make sense? Or cin, or copy, or I don't know, any data type that you use. Everything will be converted to a bunch of zeros and one for the computer to understand it. So this is very difficult to write and debug, since even a very simple program could have thousands of the zeros and ones. Just a single maybe command, right? Now, that's why we call it low level, because it is difficult to understand for us and difficult to command through 1 and 0 to the computer. We have to command it through high level, which is like C++, C, or something like that, which we can understand. Then inside the computer, it will be translated. How about assembly? Assembly is between machine and human. It's something in between. So it's between low level and high level. Because a little bit we can understand, a little bit machine can understand. Binary only machine can understand. So, but high level language, it will help us to write some commands, some instruction, some procedure, some equation, anything like that. That's why we can understand it. better than low-level language. So we need to just translate the actually human language into high-level language, and through high-level language command the computer to compile it. That's why we have compiler. To compile that to 0 and 1, then it becomes understandable for the computer. So I think I'm gonna just finish it up in here, but still any of you who has a question, just go ahead, ask your question. Then I'm gonna go through some multiple choice question. Anything? So let's just review whatever we learned today. CPU has address bus of 16 bits. It could provide what size of assembly memory? What? CPU has address bus of 16. What would be the answer? 64. In fact, it's not 64. If you calculate it, it should be exact. If you want, yeah, it's something around 65. If you want very exact, it's 65, 500, if I'm not wrong, either 34 or 36, something like that, in terms of byte. It's either 36 or 35. But we have to round it. We do not have a 65K. Therefore, the closest to 65 is 64. That's the reason. So, next is state which of this one is bidirectional. We had it even in the previous one. Data bus or address bus. Remember, I just showed you the structure. I said one of this bus is in charge of communicating directional or bidirectional. What does it mean? It simply means some of them are input and output both. Some of them are only input, some of them only output. Which one? Data bus or address bus? Data bus. Data bus is showing me which one of my registers, and all my registers in the microcontroller in the lab are connected to data bus, and then I have to say which one is output, which one is input. Kids, since I'm here in this point, remember in the lab I told you how do you define input and output inside the C? Who can remember? That could be a great challenge. Which kind of command? Yes, and please. 100% correct. D, D, R, and of course, next one is going to be the name of the port. Suppose I'm giving data direction to port P. Again, data, DR stand for direction. If this is P, this is the name of the port. So DDRP is giving direction to like register P or port P. Now, if I'm gonna turn register P one more time, this is a good review for tomorrow. DDRP. Suppose I'm gonna turn it to output. What would be my command? Yes, ma'am, please. 0xFF. And 0xFF means what? In binary, who can say? You said what? Yeah, Nicholas.
All ones.
All ones means I've got 8 bits. I have to put 1, 1, 1, 1, 1, 1, 1, 1 in all of my 8 bits to turn it to output. Now let's practice another one. I'm trying to give direction to port, suppose T. Means D, D, R, T. And I'm trying to make it input. Who can tell me how do I command my port T to become an input in C? What should I put in here?
0x0.
Yes, exactly. And what does it mean? Yeah. What does it mean if I have this command? 100% correct. Means I'm having 8 bits in here, 8 bits, or 8 bits means a byte. And then in here, since I'm turning it to input, I have to put 0 in all of them, like this. Remember it. We need to command our registers in the lab through the same command. This part of it, This is the port name. It could change and it could become different port. But the DDR is always DDR. Data direction means I'm assigning some of the ports to become either input or output. Can I bitwise a direction? Can I adjust the same port to become both input and output? This is a great question. Who can help with this? Musa said yes. What are other answers? Any other idea? Can I have a port to at the same time be both input and output through the same command? Yes. Like what? Which kind of devices could be both input and output? In the lab. In the, like all those, yes. Potentiometer. Do you think potentiometer could be output? The one that, no. Potentiometer means having a variable resistor. Potentiometer is a resistor, right? But it has the potential to give me different size for resistance. That's the difference between potentiometer and regular tiny resistors. Therefore, the answer to this question is no. It's no. I cannot at the same time turn a port to be both input and output. Right? Of course, I can bitwise the port. For example, again, if I'm having those LEDs, I can bitwise, if I have like maybe 8 LEDs in here, to maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, in the lab, I have my first LED and last LED to be loose and not connected to my microcontroller. And then the rest in middle, I can bitwise them and put 1, 0, 1, 1, 0, or whatever. But still, I'm bitwising it, means some of them could go on, some stay off, but still LED is always output. It couldn't be both input and output. First, I give it data. The LED in the lab is connected, the setup in the lab is connected to port H. So I have to say DDRH 0XFF. Means LED is just output. Output. Means just turn the entire register to become output. Then later I can mask them. I can say PTH means port H, and then I can just mask it, and either through hex command or through whatever what are the other methods I have for bitwising. Pardon? Mask. Either I can mask, or I can hex, or I can assign it to one. Just one port of it assigned to one. I introduced 3 methods during the first lab to bitwise. Bitwise means turn some of them on, some of them off, not all 1 or not all 0 at the same time. So that was a good review in here. So I'm going to pause it right in here. You're more than welcome to ask me any of your questions. Anything? Everyone good? I tried my best to review a little bit of even previous lab with you, so you have a better understanding. Before closing the session, I'm gonna just go back to Avenue while I'm here. I'm gonna just give you a little bit of understanding about what we are going to experience tomorrow inside the lab. Lab 2, I've already recorded the functionality of the lab for your reference to understand what would be the expectation. You are more than welcome to look at this tomorrow during the lab time. I'm going to also show you. We are going to look at the analog to digital conversion. And the lecture of the analog to digital conversion also, I'm going to give it to you during the Thursday session. So in here, this is exactly what I told you right now. The structure of the microcontroller, what we have inside it. I introduced the buses to you. That's why I introduced all of this information. This is going to be your pre-lab. Before joining the lab, make sure you are aware of what's going on right in here. And then we are going to have like activate temperature sensor tomorrow. We are going to learn how to command temperature sensor, how to command potentiometer. We just talked about it. How to command light sensor. I would say all of the analog sensors that we have. Remember, on top of the setup, we have temperature, we have what else? Light, and we have potentiometer. These are the sensors that tomorrow we are going to learn how, and this is potentiometer, how to command them. So this, you need to just understand maybe a little bit what we are going to do and those basic information. I've already created templates for you. I'll make them available to you. You open them, and using the same knowledge, you can just program them. This is for today. And I'm going to pause the recording in here, go through the first quiz.